Well, thank you very much. I'd like to thank the organizers for giving me this wonderful opportunity to be here. This is my first time actually in Austin. So, and also a great help for giving me this power. I just realized that my battery is dying and my power is in my hotel room. So, all right. Today I would like to focus on devices, more technology part of spintronics that I've been working on for the past several decades, and where we are and what we might be able to do and what we have already achieved. And there's a lot of physics and materials and also devices as well. So the things that we would like to address in a modern way is compute energy. This is the energy that we produce worldwide, and it's increasing approximately 2% per year. We're using a huge amount of compute energy in recent days, and if you extrapolate those energies, it looked like this. So it will cross our world's energy production somewhere around 2040, beyond 2040. Of course, this will not happen because we will not use all our energy for compute alone. So this is more realistic curves that people at Semiconductor Research Corporation anticipated. But this still means that we need to spend, let's say, 10–20% of the total energy to compute, which is still not acceptable. This is because of the data center and generative AI and all those things that we are having today. And the reason or the breakdown of energy consumption on a data center is not very clearly out there. So I can only guess, but many people say that 20% of the data center power consumption is gone to DRAM or random access memory. Particularly these days in NVIDIA, they have stacked DRAM called high bandwidth memory, and that's a source of large power consumption. And the reason why these current working memories like DRAM or SRAM that works with your computer is so power consuming is that DRAM is because we need there for density, SRAM we need for speed, but they are all volatile, meaning that you have to keep on those devices or memories all the time, because otherwise they will lose the information. And DRAM needs refresh, and SRAM needs a relatively large area. So people tend to use, for this type of purposes, DRAM, and it's volatile and it needs refresh. In order to overcome this refresh part, by turning off all the regions that we do not need. So basically what we are doing business like this today, but this is something that we would like to do in computers as well. So in order to do so, we need to have a non-volatile memory. NAND flash is not working memory, but I just wanted to put it here in comparison. There are other candidates other than the memories that I will be discussing today, but this is very promising because the voltage that needed for switching, the right voltage, is below the supplied voltage of an ordinary integrated circuits, and they're fast, and endurance is good, and so on and so forth. Okay, so these are the promises. And the junction or the device that I'm going to discuss today is a magnetic tunnel junction. I hope, well, many of you are already familiar with this magnetic tunnel junction, but This is basically made of two metal ferromagnets, green and purple, separated by very thin insulated tunnel barrier, and and this is the reason why they call it magnetic tunnel junction. And we need to have a number of properties simultaneously fulfilled, like 5 must-have properties, in order for this device to become a useful device in integrated circuit configuration. So first of all, high resistance change. These are the two resistances. Parallel and anti-parallel configuration of magnetization gives you different resistance. And these resistance changes have to be relatively large. Low switching current is obvious because you don't want to burn the whole thing. A long retention time. After all, we are dealing with non-volatile memory. Easy access perpendicular to plane is not too obvious, but we need this in order to ensure that the 2 and 3 are there. And finally, we need to have a robust annealing tolerance, which is material science. And this requirement is there because of the way people process integrated circuits, large integrated circuits. Okay, the first one is resistance change. Parallel anti-parallel configuration. You have when tunneling is not coherent, random tunneling, then it can be described by the density of state of the Fermi age, and it's given like this. And if you plug in all numbers of let's say iron or cobalt or nickel alloys of them, the maximum spin polarization is about 50%, which means that your tunnel the resistance change is 70%, meaning that you have 1 kilo ohm resistor, you can make it 1.7 kilo ohm. It's still not terribly good because you can detect it, but in order to detect and do memory operations, you have to have an amplifier or you have to wait long, and that's not good. So people come up with an idea that, oh, you can make it even bigger by using actually ordinary iron. So this was proposed by two theory groups, Bill Butler and George Merton in US and in UK, that when you build a crystalline structure oriented 001, then the decay of the different symmetry wave functions are extremely different. Meaning that if you construct this thing, then when you're looking from the right-hand side inwards, then you only see delta 1 coming out, and delta 1 is actually, even in the spaghetti-like band structure in iron, it's half metal, or 100% spin polarized. So basically, with this structure, crystalline structure, you can make iron as if it is 100% spin polarized. And well, experimentalists, of course, took it seriously and went on to see whether we can realize this promise. And indeed, remember that we only had 70% on ordinary incoherent tunneling scheme. Now we can go up to 600 or even more. Okay, and by using cobalt iron boron MgO plus annealing, we got very lucky in a sense. Mother Nature is not always mean in that regard, because here, we have this cobalt iron plus boron. Adding boron makes it the alloy amorphous, and amorphous gives you a very flat surface, and nobody has clearly understood this or explained this, but when you deposit MgO on this amorphous material, it organizes itself in highly 001 oriented structure, and then on top of this, we deposit amorphous cobalt iron boron again and anneal it. And these there will be a solid phase epitaxy starting from the interface, and the resulting structure is exactly what we wanted to have here. 001 all the way, and we get a very large resistance change. So we got lucky because the nature of this material system is such that after annealing on any substrate, actually, we get crystalline structures that we need to have. So this is a TM micrograph, just to convince you that it's indeed an epitaxial relationship at the interface. Okay, I'll skip this part. And now the switching. Again, many people already know two theory groups proposed that you can do current-driven excitation in magnetic multilayers. One by John Slonczewski, and the other is Luc Berger. And again, experimentalists took it very seriously, and they immediately, or not a couple of years later, if I may say, show that spin polarized current induces excitation and the switching. Well, at this time, in these days, people used a metallic structure, which resulted in 10 to the 8 amps per square centimeter threshold current above which they observe switching. And 10 to the 8 amps per square centimeter, for those of you who do experiments, it's extremely high current density. Usually, you end up burning the metal structure when you try to go above 5 times 10 to 8. So clearly, this is not for good application, but it showed that it's doable. Now, with this tunneling scheme that I have just mentioned, your spin polarization is effectively 100%, and which means that you can increase or decrease the switching current by that amount. And so in tunneling, magnetic tunnel junctions, usually you get lower switching current. Plus, and you also have to associate it with energy barriers that you need to overcome. So let me tell you a little bit about this. Spin transfer torque, I again assume that you already know this thing. And basically, it induces precessional motion of magnetization, and above a certain threshold current, it switches from a north pole to south pole in this case. Okay, so there's a threshold current, and now this is your threshold current. This is a barrier that protects your bits from accidentally flipping by thermal fluctuation. So clearly, and intuitively, of course, when barrier height is high, your memory is more stable, but you invest more current. And as you can see, there's an energy term, same term in the simplest possible equation here. So these are all related. But the thing is a bit different when you do experiment, because when you do experiment, you usually do on thin films, and thin films, there's a little twist here. The two energies that I have just shown are different because it has to precess. This easy axis is either left or right, and it has to precess. So yellow direction is direction that protects your bit from thermal fluctuation, but the much higher energy barrier, red, is something that you need to overcome by precessional motion. And usually the ratio of yellow to red is 10 or 100. So in-plane configuration is inefficient. You have to invest more current to switch the whole structure. So that's the reason why we need to have perpendicular easy axis, which gives you the same energy and in both expressions. By the way, this expression, although it's extremely simple, it gives you right ballpark. If you input numbers with kV of 80 times kVt and polarization of 1, it will give you somewhere around 20 microamps, and that's exactly what you see in experiment. Okay. People worked on very hard on trying to make perpendicular magnetic tunnel junction because that's the way to go. But additional, structures using iron platinum and so on and so forth didn't work at all because it may give you a perpendicular easy axis. The resistance change is very small, or you don't see switching at all. And so there was a certain period of time that people struggled and struggled and struggled until 2010. We were happy seeing that this can be actually done by not adding new materials to the structure, but making the cobalt iron boron layer thin enough. Well, the reason for this is because there's an interface perpendicular anisotropy between MgO and cobalt iron boron. And in order to use, people, well, never thought about it, but we did some systematic investigation and see how things change by thinning cobalt iron boron. And just by thinning cobalt iron boron, you get perpendicular easy axis. And that's because here's a shape anisotropy, this classical anisotropy that brings your magnetization in plane. But here's another anisotropy that has at the interface, it tries to brings magnetization perpendicular to the plane. And this is volume times surface, or volume is surface times thickness. So in order for this second term to win the first term, we have to make the layer thin. And these are 1.6, 1.0, extremely thin compared to those thicknesses that people used to use in experiments these days. We did systematic this investigation because we've been working on electric field control magnets using indium manganese arsenide, gallium manganese arsenide, and at low temperatures, and also at room temperature electric field control of iron, cobalt, and so on and so forth. But in order to see the effect, we have to make the layer extremely thin. And that's how we discovered this. Okay. Well, the reason why there's such a perpendicular anisotropy at the interface is because, sorry, excuse me. For example, iron have 5d orbitals. They have crystalline anisotropy. They're almost all fully compensated. But bringing oxygen to iron, one of the d orbitals bond to oxygen, and it will it gives and be removed from the scene, which means that and this has an in-plane anisotropy, meaning that compensated structure, we minus in-plane anisotropy, we get perpendicular anisotropy. That's how we understand this. Okay, so that's how we got single interface we can have two interfaces. Remember that the interface is a source of barrier height. So if you have two interfaces, we can increase the barrier height for 2 times. And if you make it 4, then 4 times as well. And so I'm using a very simplistic, abbreviated version, but in reality, these are extremely complex in a sense. And these are 0.4 nanometers, 0.4 nanometers repeated but for 2 times on a 300 millimeter wafers. So that's, it's surprising that people can do this at all. All right, so these are the energy barriers as a function of diameter. 30 nanometers, we get 80, and that's good for many, many applications. But people wanted to see whether we can go further in dimensions. Like people didn't like this drop of curve because it means that our technology approach is not scalable. So we came up with an idea of utilizing the thick magnetic layer, basically making it very thick and converting this minus sign to plus sign. So in this case, shape anisotropy was against us, but here shape anisotropy is with us. And basically, we made a bar magnet, very small bar magnet, and that worked very well. And of course, making it is extremely painful, and we used to have success rate of 1 in 1,000 or so. But now it's much better. And here are the results. And we can go down to, let's say, less than 3 nanometers with more than 80 E energy over kVt. And that's good for many other applications. So this is a spectrum of the magnetic tunnel junctions that we have placed. And here, these are commercially available. These are well, we have to develop, or people have to develop processing technology as well. But the good news is that the materials that you use for all the spectrum are basically the same, and you don't have to change by generation to going to next generation. You have to add new material system. That's always a nightmare, but you don't have to worry about that part until you hit to the very end of 3 nanometer scale. Okay, so 5 must-have properties we did indeed fulfill, and which made us believe that we can make STT-MRAM, magneto-resistive random access memory, and other prototype configurations, which we designed and processed at Tohoku University, my university, with using 300 millimeter spintronics lines like AI chip, FPGA, STT-MRAM, or SOT-MRAM as well. Okay, and these are, you can buy those things, or you can buy those products that have STT-MRAM. So it's no longer a future thing. And this is a smartwatch that you once charge it. I'm not a sales representative of this, but it lasts 2 weeks. I have it, but and there are other products that you can buy there. So it makes me think that it's very suggestive, to me at least, that power is a technology driver. And these are, power consumption of module versus year. And those people who are, I can see some senior faces, those who remember whether you should use bipolar transistor or CMOS for next generation supercomputer. And that was somewhere around 80s. At the time, CMOS was just a poor transistor. It doesn't consume a lot of energy, but it doesn't perform well. So the first product you saw using CMOS was a wristwatch, quartz watch. But eventually, in order to put more functions into a given area, power consumption matters. And we are using almost exclusively a CMOS today. And it's very suggestive, as I said, that this STTM was introduced on a smartwatch, which is limited energy with energy, but power consumption is extremely low. Okay, and I haven't gotten to the high bandwidth memory yet. But before doing so, let me just give you a brief detour on unstable magnetic tunnel junctions. They're still very useful. I talked about non-volatile memories, and that cannot be unstable. But unstable MTJs, magnetic tunnel junctions, are still very useful. We can design things in such a way that your magnetic tunnel junction is very unstable. This time constant is about less than 10 milliseconds. It flips up and down, giving us random telegraph noise. We can go down to nanoseconds by designing things. These devices can be used for probabilistic computing. Richard Feynman gave a talk in 1981 that quantum computing might be the way to go. But in the same talk he gave, he also mentioned probabilistic computer. And indeed, by just using 8 of those unstable tunnel junctions, we can factorize 945. This is the optimization program. And so optimization is one of the difficult tasks that ordinary computers cannot do. But we might expand this horizon to do a bigger job that is more real world related. And people have gone, this is not our work, but people have gone to this extreme and that show that they can now factorize 32-bit. 32-bit is still far away from threatening any of the encryption schemes that we have, RSA. You have to start worrying about it when we get closer to 1,000-bit, and that's somewhere away, somewhere away, but people are making a great progress on this front. So you have to watch the situation. Or now back to high bandwidth memory. Although I said we have to fulfill 5 requirements, and we did, and we do start to see products. But for high bandwidth memory or DRAM, in order to make it small, compatible, or in order to make our devices small and compatible with DRAM, we still have one challenge to overcome. Or there might be many other challenges, but the one challenge is the device size or memory size. Here, this is DRAM, comparing DRAM with STT-MRAM. I just showed that we can go down to 3 nanometers, and that cannot be done by DRAM. But the problem here is that memory size itself is 6 times or 7 times bigger than DRAM. Why is this? And this is because, for those of you who know technology, you can figure out from this cross-sectional TM. MTJs appear always on somewhere up here. And in these interconnections, you get the smallest dimension down here, and you get bigger and bigger dimension up there because you run more current on those M5, M4 metallization. And here we put MTJ on here, means that your metal that you put your MTJ on is already very big. So you cannot make it small. Why not putting your MTJ here? It's because it will be subject to repeated annealing. Every time you finish metallization, you anneal it at 400 degrees C for 1 hour. And remember the complicated structures that I have shown you? That doesn't stand. So this is, I have one more slide, but these are 5 must-have properties. And we did overcome and fulfill all the properties. And that's the reason why we do have products that we can buy. But in order to attack the HBM, we have to have a robust annealing tolerance of around 10 hours. And that's something that the community is working on. I hope you enjoyed the talk. So thank you very much.
Hideo, I have a question.
Yes.
I'm delighted to see that you are still a believer. It's good to know, okay, that somebody is carrying the battle on. You had a structure, this very complicated sandwich structure,
Yes.
which was very impressive structure, okay? But the feature size there, that was 0.4 nanometer for a metal. That's 1/10 of the state-of-the-art smallest feature in silicon technology. That's just 2 atoms. That cannot be uniform. I mean, you must have huge fluctuation in internal current, exponential fluctuation. I mean, I'm so impressed by the structure, but its reproducibility must be very, very low.
You're talking about this structure?
It hasn't come on. You know the structure, this huge structure.
Oh, this huge structure.
Yeah.
Okay.
Yeah, that one. Yeah, that one. 0.4 nanometer. That's two atoms.
Yes.
So the non-uniformity must be huge because it'll be 2 atoms, 3 atom, 1 atom. So how did it work in practice? I'm just curious. I mean,
yes, I'm curious too. I mean, it works.
But it works.
It works, and
okay,
on average,
so it's a mystery.
It's people are working on 300mm wafers.
Yeah, no,
And
I'm very impressed.
And they're talking about integrated circuits.
Okay, all right. So we don't quite understand why it's working.
Right. Yes.
All right. Thank you.